Chapter 2, Part 3. This is our last part. So we want to know, why do we see the different phases of the moon? So lunar phases are a consequence of the moon's almost 28-day rotation around the Earth, 27.3 days to be exact. So the phase is because of a different angle of a reflected sunlight with respect to where the observer or where the person looking at the moon is located. Let's say that this is the observer, or this is the person that's looking at the moon, and the moon is exactly between the observer, which is on Earth, and the sun. So this is towards the sun, and the sun is an exact, or relatively exact position. So this would be the new moon, or the observer would not see anything in the night sky. As the moon rotates counterclockwise, we go all the way from waxing crescent, first quarter, waxing gibbous, full moon. The full moon is exactly happening when you have the moon on the opposite side compared to the sun. So sun is here, the moon is over here. Okay. Waxing gibbous, waning gibbous, third quarter, and waning crescent. So these are the different phases of the moon, and it's because it's uh, relative to where we are on Earth, what time we have, what part of a month we are. Uh, Moon is reflecting a portion of the light from the sun, and that's how we see it. So let me go ahead and play this little thing for you. So, all right. So here, let's say that I want to go to the new moon, okay? And let's see the view of on the Earth. You don't see anything. You see darkness because this side of the moon is complete darkness, and this is where the sun is, okay? All right, so if I bring the moon here, this is what I would see. You see a tiny portion of it is visible to this observer, so that's why we see it like that. First quarter, full moon or second quarter, third quarter, and again the new moon. Okay. Now let me go back to the PowerPoint. So new moon, crescent, first quarter, gibbous, full, gibbous, last quarter, crescent. So this is called waxing when it is going to the full moon, and it's called waning when it's going to the new moon again. In this part, moon is visible in the afternoon or in the evening. So every time that it's in the afternoon or it's in the evening, the sun is about to set, it is waxing. And if it is, you see it in the late night or early in the morning, that's where the waning is. Okay. Thought question. It's 9 a.m., so it's in the morning. You'll look up in the sky and see a moon with half its face bright and half its face dark. What phase is it? Half its face dark, half its face um, half bright, half dark. Now, it's 9 in the morning, so you're seeing it in the morning. Okay, you're seeing it in the morning. So it's right here, it's waning. So it is one of these. So let's take a look. Third quarter, okay? Or last quarter, third quarter. First quarter, second quarter, third quarter, or last quarter. Half of its face is dark, half of it is bright. Now, we only see one side of the moon. We don't really see the other side. And if you're looking at the map of it, the map of it, the names of those features on the back side of the moon is all in Russian, because the Russians were the first people to send a spacecraft to study what's behind the back of the moon. But we only see one side of it. It's because of its synchronous rotation. The moon rotates exactly once with each orbit. Okay, and we will talk about it. What happened to the moon later on? What happened to the moon that it stopped rotating? It used to rotate just like us every 24 hours. It used to that we rotate. It used to rotate, but it doesn't anymore. And we will learn why and what happened to it. But only one side of it is visible. The other features related to the moon is that it can cause eclipses. Okay, uh, if you have Earth between sun and the moon, that's called lunar eclipse. And if you see the shadow of the moon on Earth, it's called solar eclipse. But regardless, it is related to the orientation of moon, Earth, and the sun. If it is in the full shadow, it's called umbra. And if it's partially shadowed, it's called penumbra. So let me go to this. All right, so if I change my orientation, okay, so we are completely on umbra right now. Okay, this is the sun, this is the earth, and this is the moon. And this is what you would see because you are looking at the shadow of earth on the moon. And if you're in between, you would see something like that. And if you're completely on penumbra, you would see a little bit of a shadow, but not too much. If you're outside, you don't really see anything. The same is true for solar eclipses. When you have the shadow of the moon on Earth, and we saw it, and we had one great one actually in the United States back in 2017. So I'm gonna just play this, and you know what I'm talking about. Let's say that you are standing on that red dot here, right there, and you can kind of see the shadow of the moon covers your spot on the top picture right there. So it's basically moon is blocking the sunlight for us for a few minutes or a few seconds at least. You can see that it is complete darkness. You can see the dark, in the darkest sky, you can kind of see the bright stars, but that only lasts for a few minutes and then everything back to normal again. Okay, so the lunar eclipses can occur only at full moon, okay, because moon is in the opposite side. If this is Earth, moon and sun are in the opposite side of the Earth. Lunar eclipses can only occur on full moons. Lunar eclipses can be a penumbral or partial or total. So we just talked about it. Solar eclipses, we just play that video, but we all, I'm pretty sure that most of us have seen it at least once in our lifetime so far. Um, you know, we had it, as I said, in August 2017. The solar eclipses can only occur at the new moon. Okay, solar eclipses can only because you have sun and the moon on one side. But the question is, if this is the case, if new moon and full moon can cause solar and lunar eclipses, why don't we see it happen every month? Why it's usually few years and then you have to wait a couple more years, maybe a decade for it to happen, and you can kind of see it. If this is the case that new moon and full moon will cause solar and lunar eclipses, why don't we see it once every month? And the answer is because the moon's orbit is tilted about 5 degrees with the ecliptic plane. So if this is the ecliptic plane, or if this is the path or the orbit of the Earth around the sun, this angle, this angle is 5 degrees. This is the orbit of moon around Earth. This angle here between moon's orbit and ecliptic plane is about 5 degrees. And that causes to not have a solar and lunar eclipse once every month. But instead we have seasons for lunar and solar eclipses. We have 2 eclipse seasons each year, lunar eclipse and solar eclipse. So just to give you a summary of the conditions to be satisfied when we're talking about the eclipses, it must be a full moon for a lunar eclipse or a new moon for um, solar eclipse. And the moon must be at or near one of the 2 points in its orbit where it crosses the ecliptic planes. So back to here, um, it has to be here, which obviously this will not cast any shadow. Here we'll have a full moon near, we'll have a lunar eclipse. Here the moon does not cast any shadow because of its orientation. And then here we'll have another full moon near the knot, which cause a lunar eclipse. So 2 conditions should be satisfied. First, full moon for lunar eclipse, new moon for solar eclipse. And the moon must be at or near one of the 2 points in its orbit where it crosses the ecliptic plane. Where it crosses the ecliptic plane, meaning that it does not have it doesn't have the 5 degrees orientation anymore. This point and this point. So we have seasonals. We have seasons with for lunar and solar eclipses. Here's a path for or the cycle, which is about, as accurate as you want to take a look at it. So the next one, so the last one that we had was in August 21st, 2017. We will have another one in April in 2024. April 8, 2024, which I believe it will also cover Missouri and probably in St. Louis. So the knowledge that we have, and we were talking about the ecliptic plane and the lunar eclipse and solar eclipses, the knowledge that we have, we it's not a fairly new knowledge. Asian people knew about some of these stuff as accurately as we are talking about them today, thousands of years ago. They knew that Jupiter, Saturn, Mars, Venus, and Mercury, they're all lying in the same plane. This is the ecliptic plane. This is all of these are lying in the same plane, or they are all sharing the same path in the sky, in the night sky, and we call it the ecliptic plane. Sun is also having the same path, but obviously when it's out, you can't really see anything. It needs darkest to see all of these other stuff. But the point is, it is not a lot of people knew about these. Asian people knew about the orientations of these stuff. So, but something that they could not explain is that when you're looking at the path of some of these planets, they tend to start from west, going to east, and they go back. So here, for example, in November 3rd, 2011, is the path of the Mars. It starts going towards the east, and it's getting here in January 23rd, 2012, but it's going back March 2012, April 2012. It's still going back towards the west, but it suddenly stops here again and going back towards the east. And July 2012 is where it's going towards the east again. So you have this weird shape type of motion in the night sky. And just people could not explain this. Asian people, people's living 400, 500,000 years ago, they were looking at these. Obviously, they had nothing better to do, right? So they were looking at a night sky. That's the best entertainment that they could have, to start a fire, and then eat something and then take a look at the night sky and enjoy. So they knew, but they couldn't explain why this is happening. They knew that they are all sharing the same type of plane of motion, but they didn't know why they see something like this in their orbit. And this is called the apparent retrograde motion. Okay? So we see apparent retrograde motion when we pass by a planet in its orbit. In other words, if this is Earth orbit and this is Mars orbit, on point 1 we see Mars right here in Gemini. In point 2 we see Mars here in point 2. On point 3 see Mars on point 3. On point 4, when we are passing the sun, when we are passing the Mars, we see that apparently Mars moved from point 3 to point 4. So it was going from 1, 2, 3, but it went back. It went back to the west, and they couldn't explain this. It's because it's exactly about the time that Earth passes Mars in its orbit. So going from 4 to 5, we see Mars at point 5, and then 6, 7, we see him in this position. So it started from west, 1, 2, 3, and then it went to east, but it went back to west again, and now at point 5, it's going back to east again. And it's called apparent retrograde motion. So easy for us to explain because this occurs when we lap another planet or when Mercury or Venus laps us. But it is very difficult to explain if you think that Earth is at the center of the universe. So people 500 years ago, people 1,000 years ago, they didn't know that the sun is at the center of our solar system. They thought that Earth is at the center and everything is rotating around us. So it's very difficult to explain what is happening to the path of the Mars or what is happening to the path of the planet with the idea of sun not being at the center and Earth being at the center of the universe. It's really difficult. Okay. The other thing that they could not explain, or they actually rejected or the Greeks actually rejected, because Greeks were the first people who were thinking about these stuff. Why they rejected the true explanation of what's happening, or the true explanation of what's happening is sun being at the center and Earth is rotating around the sun in an orbit. Okay, why did they reject it? Because they could not see stellar parallax. And what is a stellar parallax? Let's say that this is Earth in January and you're observing a bunch of stars. So you see this a star with respect to the fixed background of the stars, okay? Kind of like that. This is what you would see. This is star with respect to the fixed background is this. 6 months later, in July, you're looking at the same star with respect to the fixed background, and you saw that its position has changed. It was here in January, now it's moved to the right in July, 6 months later. They couldn't see this So they thought, okay, maybe we are in the center of universe, because if we were not in the center of universe, we would be able to see these stellar parallax. In fact, in order for us to see a stellar parallax, we need to have a telescope. These stars are really, really, really far away, that in order for us to see and comprehend and understand a stellar parallax, we need to have a telescope. Ancient people did not have telescope. They did not have the technology. Because of the lack of a stellar parallax, they thought, okay, we don't see a stellar parallax, so thus we are the center of universe. Okay? So that was the reason that they rejected the true explanation of sun being at the center. So stars are so far away that the stellar parallax is too small to notice with the naked eye. You need a telescope, as I said. Earth does not orbit the sun. It is the center of the universe. That's what the ancient Greeks, or the ancient people were thinking about, or that's what they understand. And as I said, um, so this causes a stage to set for a long historical shutdown between Earth-centered and Sun-centered system. Okay, so this is the end of chapter 2. We will talk about this in details, and what happened to the people that were thinking about these type of stuff, what type of theory they had, why is it called um, retrograded motion, who invented the theory that could explain this. We will explicitly talk about this in the next couple of chapters. Okay, so stay tuned for the next chapter. This is the end of chapter 2. I hope you enjoyed it. Let me know if you have any questions. Okay.